There we go. And there's my don't be late alarm. All right. Well, it's 8 o'clock and we can go ahead and get started, everyone. Today's class, I will say, is maybe a little unorthodox, but hopefully will teach you about some really good, useful resources out there that are able to support you in your conversation about air barriers, water resistive barriers, and vapor retarders. So these are sort of the holy trinity of what we work on the energy code on a regular basis. Specifically, it's the kind of things that we look at in our total and complete holistic look of our wall assembly, because all of these things are typically related to each other, but with some key differences about their different roles, their responsibilities, what materials you can use for them. And oftentimes, the reason that we highlight these together is because they are tied together by people who are saying one thing meaning another. This language gets overused in a way where it's one of my first plan review bosses I ever had told me, Andre, words mean things. And I always took that to heart because we aren't speaking the same language, then all I'm doing is giving you essentially bad advice, right? Telling you you need to fix this on your plan, but if I'm not educating you in understanding exactly the words I'm using to refer to a particular item, then we're going to end up always missing the mark and we're going to spend more time working through this than maybe is completely necessary. So, in large part, that's kind of the big stuff that we're going to talk about today. Our agenda here is going to look like this. We're going to talk about some overview of construction components. We're going to talk a little bit about the stuff that Josh usually does have for you on a regular basis, about the form and function of the code and why it's built the way that it is. So I know that that's a key component he likes to keep up on every webinar, and I won't let you down by taking it out. We're going to talk about the definitions of each one of these products in the code and how it relates back to the way that we're going to think about enforcing them. We're going to talk about any code updates for these, kind of what's changed over recent years, so you kind of know what is here, what may be coming down the road. And then we're going to get into the meat and potatoes, which is that resources component. So I'm going to try and kind of walk through these kind of, I'll say, briskly in order to be able to get us through all of the stuff that we have for today. So Josh likes to start out with a slide, and I really do like it. When we understand the why, we can figure out the how, right? If we know why we're going to do something, the intent of that code, then we can navigate the issues that come up when we are trying to figure out the nuances about how to approach it, especially when we talk about systems like this, where, when we talk about air barriers, one of the things that's going to come up quite a bit is the quality of the installation is directly proportional to its effectiveness as an air barrier, right? And I know that that's kind of the case for a lot of things that we look at, but there's a lot of things that I have, as an inspector, given off approved the C minus. I would never frame that way, but it's braced and it's holding and it is technically valid according to the code. And so I cannot tell you no, it is invalid, right? We often like to assess that we're not quality control inspectors, so to speak. We are talking about the code as a bare minimum standard, but in the energy code in this space, it doesn't always line out that way. And so this is one of those places where understanding the intent of what it's supposed to do helps us understand why that's looked at a little bit differently and why you have different tools and resources in the 21 and in New Mexico with like your thermal bypass checklist and your visual inspection checklist, right? So being able to really understand the intent of why this stuff is in the code is going to help you be able to enforce it effectively and get people, I'd say, confident in their ability to pass things like their air barrier test, and yeah, their air leakage test, their blower door test, all of that good stuff. So let's talk about the purpose statement, right? So again, we're going to kind of drive home on that. We enforce minimum requirements, right? That's out of the IBC, the IRC, and accordingly, the energy code itself is a minimum standard component, or at least it's meant to be that way. It's meant to be that bare minimum standard. And what we really want to highlight here, really emphasize is effective use and conservation of energy. One of the intents here is to make sure that we make a wall system that is going to be durable and long lasting. It's going to protect the insulation inside of it, and that insulation is going to be able to do its job effectively. And that's why these components really tie together in a manner that's really important to understand effectively and how they do that, how they overlap your insulation, your vapor retarder, your air barrier, and seeing that each one plays a certain role is going to guarantee that we're getting the most out of that wall assembly because all of this is passive, right? This is the same thing a lot of times in my mind when I try and teach this. What I talk about is that, like, we know that there are active systems for fire prevention, right? We can talk about things like a sprinkler system. That's active prevention that we know is going to typically work in the circumstances that it's meant to. And it's expensive, but it's also going to put out that fire. It's also going to do some water damage in the process, typically, but it's going to put out that fire. When we talk about passive systems, which the code has always been responsible for a very long time now, we're talking about our cheapest, most durable means to effectively provide fire protection throughout a building. Well, similarly, in the energy code, yeah, there are a lot of ways that we can think about energy code in terms of trying to reduce energy use, but one of the cheapest and most effective means is just building a good wall, right? And understanding that process very well. The other thing that I want to emphasize here is the flexibility component. The flexibility component is crucial here because you're going to find that a lot of these different components can be put in different places in the wall assembly, right? And different products can serve one or two purposes within this system. So as we talk about this and kind of break into this, that leads us directly to innovative. So those things are really linked in this space where we have a lot of flexibility, even prescriptively in the code for the products that you're allowed to use and the way it's going to tie back to your insulation systems as a whole. So this is a nice quote that I really like when we talk about this and really start getting our head around, okay, we're thinking about the wall holistically today, and we're going to be thinking about these three components in it and how they work, which is that residential construction is a complex operation, including thousands of processes, dozens of industries, bringing together hundreds of components and subsystems into a house. And there's no better example in my mind than looking through all your barrier systems because you have penetrations through all of these components, but only one is going to serve as the air barrier, which means that's the one that you have to seal to. But meanwhile, you also have to flash for water intrusion and these other parts. You have to match up the right products, right? That can be things like thermoply and foam sealant in order to be able to create an air barrier. Those are two products that you're marrying together in the field, and you're looking to make sure that you're not violating either of the manufacturer installation instructions to create the assembly that you want, for instance, right? So you're looking at all these different individual products, some of which are definitely designed to be tied together, right? Think like Tyvek and all of its tapes and sealants, right? Everything that's proprietary in that space, versus instances where you're doing it yourself. That could be taped sealants, that could be foam sealants, and then plywood or OSB. That can be part of your air barrier assembly, right? That can also be our stuccos, right? That can be our adhered masonry veneers. There's multiple ways to think about this, and each of them has a role to play in this assembly. So here we are at a nice breakdown of kind of all of these components as we can see them in real life. From the left to the right, we see our framing, we see our sheathing, we see our insulation, our cladding, we see all these things getting tied together. And then we see some of the other finishes that we might have. Interior, we'd have maybe drywall, we could use other stuff. Drywall's super common, obviously. We could also see our water resistive barrier. That's going to be our Tyvek house wrap. We can see our, foam board insulation being used on the exterior, and that's going to provide more than one service to that building. We can also see our vapor retarder in our craft facing. And each of those components is all part of this big assembly that the EEBA quote was kind of referring to and talking about. So let's talk about the three big definitions here in each one of these, what we're talking about today, right? So a water resistive barrier is going to be effectively acting as our drainage plane, right? Or a component of our drainage plane. It's going to be that material behind the exterior wall covering that's going to resist liquid water. And that's a key feature of this conversation, the liquid water component, which has penetrated the exterior, and we're stopping that from moving further into the assembly, right? So remember, this is the weather on the outside. This is the exterior water intrusion. It's not the same thing as the water we're going to make inside the house, right? We're going to have steam and humidity. We're going to have those things happening on the house on a regular basis. That's not that water. We're talking about liquid water that's not in that vapor format, but that driving rain that might be trying to penetrate the assembly. Now we're talking about that when we go to vapor retarder, right? So now we're talking about permeability of moisture in a vapor format, not a liquid format, a vapor format, right? To be able to pass through the rest of this. Richard, I see you're asking if the slides are available. You bet. I will make sure that before the end of this, and don't worry, you're going to get a whole lot of resources from me today, but I will put them in the chat for you, so you'll be able to take them with. So this is going to be the ability for moisture to penetrate through other materials, right, and coalesce. So this is when we're saying, okay, we know we're going to create moisture on the inside of the building. We also are sealing this thing really well, right? That's our air changes per hour. We're also doing our best to be able to seal in this exterior component. So now we got to tell this water where to go because we don't want it just collecting in the wall cavity environment, right? We don't want it just hanging out there to create mold, mildew, rot, any of those problems. And then we have air barriers. And air barriers, I want you to think about our systems. There's almost no air barrier. There are a couple. I'll make the caveat right now, right? Your spray applied fluid stuff, right? Because it's acting in more than one facet, right? It's acting originally as a liquid and then it solidifies into more of a, like a flexible solid, basically. But what I mean by that is that any other material that you use typically as an air barrier is going to be more than one material. You're going to be taping joints and seams. And this is where that effectiveness in the installation is really related to its ability to do its job over the lifetime of the building, right? So that's why it says one or more materials joined together in a continuous manner, right? That's really giving that input that those are systems, and we're thinking about that airflow, restricting that airflow through the passage of the thermal building envelope and its assemblies. So we're thinking about how this is going to join in holistically. And remember, building thermal envelope is encapsulated on all sides. It's six-sided. It's every side of the building, right? That's full and complete. If we're leaking air in any place, then that diminishes our ability to say that we have a complete thermal envelope. And so this is really tied together at the hip with where insulation goes and where we define that exterior thermal envelope. So let's talk about some examples of these, right? So in this particular instance, I really want to highlight that insulation and air barriers really work together. And so what I have for you here is a cut detail to seal a rim joist with 2 inches of closed cell spray foam. Right now, we're going to get into the specifics of this in the code, but I want to highlight this as a really good example because we know this is a tough joint to seal, right? Rim joists are notoriously difficult. They're terrible for air intrusion, right? And so it's one of the places that's specifically highlighted in 402.4.1.1 that we're saying, hey, we really have to get a detail on how you're going to do this and explain your work. Show how you want to do it. And the 2 inches of spray foam is going to be enough to become air impermeable. So not only are we getting the insulative value out of that spray foam, right? We're taking that R value and we're saying this is fighting thermal conductance in this space, but we're also getting the air sealing qualities of spray foaming in that rim joist, right? So now we're going to be able to say, okay, it's covered completely with insulation and it's creating that air barrier, which gives us the total thermal envelope continuity at the rim joist. I think it's a really good example of seeing these two work in action. Another good example here is your vapor retarder and your insulation. Now, the reason I have exterior insulation here is because remember how we talked about dew point, right? We talked about where that moisture is going to come from a vapor on the inside of the building and it's going to coalesce somewhere. And depending on where we put that air impermeable insulation, if we're going to be using that in the wall cavity, is really going to determine for us where some of that wants to collect because that can act as part of the vapor retarder assembly. So as we use continuous insulations more robustly and more prescriptively in our designs generally, we have to think about its relationship to our air barrier. Because if I air seal on the exterior and it's completely impermeable, and I also put a vapor retarder in that's so stringent that it won't let any moisture permeate the other side, well, no matter what happens, I know there's going to be moisture that's going to coalesce in those wall cavities, right? And if I didn't tell it where to go, then it's just going to hang out there. And that is where we start to develop those issues. So these two are really joined at the hip and work together in a really important format. So I'm going to go through these next sections kind of quickly because I know you guys have gotten a lot of this education before. So hopefully we'll be reiterating some of the stuff that you already know, but I want to meet everybody where they're at. So if you feel like I'm, moving too fast or you want to take a moment for a question, please feel free to stop me. But otherwise, we're going to hit this kind of where it's most important here, which is looking from the exterior, right? We're going to talk about air and water intrusion, right? Now, water is part of that water resistive barrier assembly when we talk about its infiltration into the exterior wall assembly, right? Now, the rest of the time, though, we're also talking about air sealing. And that's going to become really important when we talk about that thermal envelope. So these two have a relationship as well to each other. Now, moisture is the number one concern that almost all of us have, right? Where nothing's going to make a homeowner more upset than getting that phone call saying, hey, you have rot right underneath your windowsill or something like this, where they open up that wall cavity and they go, oh my God, look at this. This is completely useless now. I have to mitigate all of this. How far does the mold go? How structurally damaged in this? Moisture is a major problem. And not only is it structurally a problem, but if you think that insulation is doing okay, after it's been wet and heated a bunch of times, all that moisture is compressing that insulation naturally, it can't do its job either. So there's going to be multiple telltales of this failure occurring in this assembly. So when we do a small amount of wetting repeatedly, we get that reduced R value, like we were talking about. We get that mold and mildew, we get deterioration and rot. Now, those water sources can come from water infiltration, as in bulk water, right? So that's rain penetrating. That can also be a problem from vapor diffusion. That's the other side of the wall assembly, right? Where we get that condensation, right? Condensation occurs because we have a disparity between temperatures, right? That's why your Moscow Mule mug gets really wet on the outside on a hot summer day because it's cold on the inside, hot on the outside, and all that moisture in the atmosphere wants to condense to the sides of it, right? And so when there's a temperature disparity, that's when condensation occurs. And remember, the point of a good thermal envelope is to create temperature disparity, to not be the same temperature on the outside as it is on the inside. So this is a problem we always have that's endemic to what we're trying to do just based on physics, right? And then air movement, of course, right? Air movement can always bring moisture with it. The more air can penetrate through the assembly, the more moisture that can come with it. So let's talk about phases of water, right? We already talked about the fact that you have to worry about liquid water. We also can get solidified water, right? So as it turns to ice, that's going to kind of change our approach to this. That's why we get certain materials like ice and water shield or ice barrier, depending on, if you go with the name brand nomenclature, if you're really specific on the code language there. Our materials are designed to fight this intrusion because we know once it gets in, it just kind of keeps repeating on a feedback loop, right? Where once we get liquid water in and it freezes, well, water, when frozen, expands, right? Once it expands, it creates a bigger hole. Once it creates a bigger hole, we can get more water in. Once more water in, it's going to freeze again, right? It just keeps on going on this loop where it's going to create this problem in perpetuity. And then we get vapor, of course. And we've been talking about vapor a couple of times here because we have specific parts of the assembly that are meant to fight the vapor issue and tell it where to go specifically. But we're worried about all three of these when it comes to our walls, right? And so when we think about controlling for water, we want to make sure that we're controlling for moisture entry, controlling for that accumulation, and then we're showing that water where to go. We're trying to get it mitigated out of the system. Now, the ideal circumstance, right, is to prevent water from intruding in the first place, right, and prevent any assembly from getting wet on the interior. But we also know that there's some places that are always going to get wet in the interior, right? Think of your bathrooms, right? Think of your kitchens. Think of the places where you're boiling water and that vapor is getting up to the ceiling, and there's only so much you can do. You've got your mechanical ventilation, and hopefully it's right size to be able to take that out. But if your family's a bit like mine, they don't always want to run that fan all the time. Sometimes it's a little loud. And so sometimes there is a boiling pot of soup or pasta that is going without any fan to alleviate that moisture. Sometimes that's just the way humans are as creatures, right? We also are going to leave windows open at times where maybe it's less than ideal. Human beings also give off moisture. We're going to go over a couple of these things. But then if they do get wet, and they will get wet, we need to make sure that they're able to dry out. And that's the really big and important part of this. So now let's take a look at the code language itself. We're in the 21 IRC, right? And we're looking at water resistance here. So as we look at water resistance, we see that the first thing that we really get is an explanation that says we're going to design the wall assembly in such a way that we're going to make sure that we're going to prevent the accumulation of water because of the very same things that we've been talking about. Once it gets in, it's really hard to do that. We're going to do that with a water resistant barrier, which is highlighted right here. So we're going to use that as part of the means to provide draining of that exterior water. Well, that ties directly to the drying effect there, right? If it can drain out of the assembly, that means that the assembly can get airflow to dry off while still preventing penetration into the rest of the building. That's why your water resistant barrier is going to tie very neatly and very importantly to your exterior wall coverings and your flashings, right? Because those are all going to work together to create that continuous weather water resistive barrier that's described in 70311. So in order to do that, we use water resistive barrier. We can also use a roofing underlayment. That's a perfect example of doing that just from a different direction with different materials. Capillary breaks is another one, right? So that's going to be things like our sill seal and ways to prevent that moisture from the concrete from penetrating into the rest of the assemblies. And then water and damp proofing, right? And that's why we're going to get some specifics later on about our vapor retarders when we talk about some of these damp areas like crawl spaces, places like that, is because we already know that there's typically going to be water and damp proofing. We also know that we don't want to trap water and create those circumstances again where we're creating that feedback loop of water intrusion, but not exfiltration. We're not getting it out. So we definitely don't want water to become solid in our assemblies. We talked a little bit about that. We want it to really prevent from entering at all. And if it is liquid, we want it to drain away from the assembly. And we're going to use insulation and air barriers, right, to prevent that intrusion, especially from a vapor component as it changes latency. We're also going to use our water resistive barrier in order to prevent that from happening. Now, bulk water tends to find the path of least resistance, but it doesn't always follow gravity. And a lot of folks, a lot of good inspectors that I know that have been in attics looking at how on earth is, are you getting moisture up here? And then you start to realize that it might be a condensation problem. It might be that water is running laterally across a shingle. I've had that happen a couple of times from valleys that weren't clipped properly on the edge, right? Things like that, where you get water that uses the capillary effect to sometimes work in ways that are surprising, that might work against gravity because it is still the path of least resistance for that water to follow. And here we see some examples of that capillary effect into the concrete and then where it's getting trapped into maybe basement or crawl space insulation. We also see instances of damp proofing, right? So this is where those places really do matter for us to say we've got that continuity of water resistive barrier. In 703.2, we get a little bit more language. We get a little bit of information here that goes over a water resistive barrier to be applied over studs, flashing, and for continuity, we get some materials that it's allowed to be as well. We also get identification if you're using stucco and adhered masonry veneer of where to go to for additional information on that water resistive barrier. Now, a lot of this is, not surprising for people. We've been using 15-pound felt since, forever. Carpenter's been using that a long time. It's still used on roofs to this day. And then we also get our ASTMs or our testing to be able to say, okay, these other items that some manufacturers might want to put out there and say, we can use this as a water resistant barrier. Great. You can point to those particular items and say, okay, we've got the information necessary to move that forward. Here's an example of one of those kind of two-part systems. And for this, a great resource out there is the Portland Stucco manual. It goes over sort of your different, hard coat, stucco finishes. And then it goes over the water resistive barrier versus the bond break component of it, which is why you get those two layers of paper, between the chicken wire there, that lath. But it basically gives a good explanation of how that's supposed to work in the overall system. But here is just, a rough breakdown of what that's going to look like, where we see that a drainage plane is created with effectively two layers of water resistant barrier, typically this felt paper when you're using stucco, right? And so we see that identified on both sides of this because we want that ability to dry in the drainage plane. Again, we want water, if it's going to make it through here, which we don't want it to do in the first place, we're going to give it a highway. We're going to tell it, okay, on your way, go down, use gravity, get out, and then the flashing helps direct that fully away from the foundation system. Now we move on to vapor retarder. And we're going to cite basically our wall sections here in 7027 and 1404.3, respectively, if you're in the IRC or the IBC. But a lot of the principles here are going to remain the same. That's one of the best things about, I've got to say, teaching this class and going over this topic, is that the building science is really the same no matter whether you're doing residential or commercial. And you'll find that some of this stuff has a lot of overlap in the way that it's identified in the code in terms of materials. A lot of the materials are the same that we use, whether it's residential or commercial. But ultimately, especially with vapor retarders, the principles of planning out where your impermeable insulations are going to be, what your vapor retarder type is going to be, those all coalesce the exact same way. So earlier we talked about classes of vapor retarder, and that was based, like we said, on permeability. Well, permeability is how much vapor a material can transmit over time. And so that's why we get this sort of description in what feels like an equation down here, but I'll explain kind of each bit of it. So the first thing that we talk about here when we look at this is ASTM E96-05, which has become the standard test for water vapor intrusion, right? And so this is what you always look at to say this is, an approved material for acting as a vapor retarder, and then you use this amount of permeability based on that test, because that's what it's really giving you here. And so grains, for our folks that are, maybe precise measurers, maybe they do reloading, maybe they do stuff like that. A grain is an exceptionally small measurement. It's a very, very little amount, right? So we're talking about grains of water, and a grain of water is an almost infinitesimally small amount of water. Let me tell you. I've got a little bit of a breakdown of this moving forward, but it's an exceptionally small amount. Then we have to look at an area. We have to say, okay, when we're talking about the ability for water to pass through, water vapor to pass through a material, so it's effectively penetrating that material. We need to know the area of material that we're talking about. So we say feet squared, right? We have a unit, we're going to use it. Then we say per hour because penetration over a material takes time, or through a material takes time. And then we say inches mercury, that's inches Hg, and that's because we need a standardized pressure to be able to say that that's how much of that material passed through, right? If I increase the pressure dramatically, right, inside of, say, a vacuum, I can pull little droplets of moisture through just about any material very quickly. But that's not the question here. We're talking about passively in a wall assembly, how much of this is going to happen regularly over time. And so we get all of this together to say, okay, that's how we want to figure out how much permeability a particular material has. And so here's some examples of your typical vapor retarders and their different permeability ratings. So craft face insulation qualifies as a class 2 vapor retarder, and puts it in that 1.0 category here. And so below that, we're going to start getting into the stuff that's, more and more restrictive. This is like a golf score essentially, right? The lower that number is, that means the less material is passing through there. And so it's more effective at doing its job. That's why I say golf score, right? The lower the number, the more effective the material is at doing its job and preventing moisture. So you might be wondering, well, why don't we all just use aluminum foil or polyethylene, right? Polyethylene's cheap and it's really, really good. It's doing its job. Look, it's at the bottom of your list. Well, once again, it's really good at being impermeable. And if we know we're getting water inside the wall assembly, and we have impermeability on both sides of that wall assembly, then we have made a trap, right? We've essentially told that water you have no place to go, so this is where you live. And that is not for our best interest. That's why the code is really specific about breaking down, okay, you want your class of vapor retarder to match the assembly of your insulation. So here's the breakdown of the IRC, right? Class 1 is very low permeability, right? Rated at 0.1 perms. So that's things like our polyethylene or visqueen, right? Or aluminum foil or Class 1 vapor retarders. Low permeability vapor retarders, that's at Class 2. That's why I said it's in the middle for you guys, right? Is that craft facing would qualify as a vapor retarder in a Class 2. Plywood could also do that, or OSB, right? And then we get over to our medium permeability vapor retarders, which are rated greater than 1 perms, but less than 10 perms. That can be our latex paints, right? And so you'd be wondering, once again, like, why wouldn't you want something that's the most impermeable thing you can get there? Well, again, we know we're going to get water in this material. Can we get it out? That's the most important thing. So like I said, human beings are messy creatures, right? We're going to boil water. We're going to boil pasta. We're not going to put the fan on when we do it sometimes. We're going to take hot showers and maybe not always turn on the fan, or maybe that fan isn't effective enough to get all of the moisture out to get that area dry. It means we're going to have some latent moisture in there all the time. We just give off some humidity as a whole, and we also like humidity, right? Some of us will add humidifiers to our heating systems because we like a little bit of ambient humidity. Your Manual J tests your furnaces at 50% relative humidity. And so it's important to recognize that You're always going to have a little bit of moisture on the inside of this wall assembly. We also like plants for the most part, right? Or we have pets. We have other things inside the house that are also going to create moisture. And there's our humidifier, for instance, right? So that's a creature comfort issue. So when we talk about vapor diffusion, we're talking about basically one of the rules of physics, is that everything in the universe wants to normalize. So all of the water molecules over here, they want space. They don't want to be bumping into each other all the time. So they want to diffuse through any other material to have as much space as possible and normalize so they're everywhere. They want to take up all the space that they can and be everywhere. And so vapor will basically vapor will use pressure to push water through materials at a microscopic level. And it's a function of temperature and relative humidity. Remember how we talked a minute ago about the inches mercury, the feet, right? All of those parts of figuring out what permeability is, that's why it's measured the way that it is, and you get the perm rating that you do. And so here's our diffusion problem in action. So here we have a 4x8 sheet of drywall. Now this test was done by a gentleman by the name of Joe Stebrick. He writes a really good article about it, and he basically describes, okay, at an interior temperature of 70 degrees and 40% relative humidity, over the course of a year, you're going to get about half a liter of water over here, right? Through this material. So 4x8 sheet of drywall, that's how much is going to pass through that to the other side. Now remember, this is just drywall, right? We can talk about the other materials that you would use, but remember, all those materials are recognizing this is the natural state of just moisture passing through a material, which means we're always going to have some moisture that's entering the wall assembly. Are we going to tell it where to go effectively? But if I cut a 1-inch hole into that drywall, look how much water passes through the other side. It's something along the lines of about 30 to 36 liters of water can pass through that in a given year. And it's not like he's holding a hose to it. That's just ambient relative humidity at 40% passing through that. Now, I know what you might be thinking. There's large swaths of New Mexico that are very dry. There are large swaths of Colorado that are similar too. And I do understand that, but there's no getting around the fact that we have seasonality, we have changes with that. And the reality is that even if you're in a drier climate, we still know that we're going to have people that are creating humidity inside your buildings. So are we planning effectively with our vapor retarder systems in trying to mitigate that? Well, we have an example over here, right? Once we get to 7027, where we start looking at some of these items, and we see that we have some exceptions for our vapor retarders for class 1 or class 2 for basement walls, below grade walls, and construction where moisture or freezing will not damage walls. And this is one of those really key or important places to look at because we're recognizing that a lot of the exceptions I identified here are the places where we're going to have the most moisture, right? Or most natural moisture. And then class 3 vapor retarders, well, we get a chart. We get a very nifty chart here in 7027 that goes over, okay, depending on where you are in terms of climate zone. So let's look at just climate zone 4, for instance. We have vented cladding over wood structural panels, vented cladding over fiberboard, right? These are places where we're allowed to use our class 3 vapor retarder. And then we also have continuous insulation identified. Again, because that continuous insulation will act as a place for moisture to condense, it is a place that we want to align where we're putting that vapor retarder at. And now we're moving on to air barriers, right? So air barriers, we're just looking at the overall definition where we get it from the code. And so our air barriers are one or more material joined in a continuous manner to restrict the passage of air through the building thermal envelope and its assemblies. So again, we're talking about that overall systems look. Now, good question for y'all. When were air barriers first introduced to the code? Any guesses? Toss them in the chat if you have one. Any guesses? When were air barriers first added to the code?
Pick me, pick me.
Hope, what do you think?
Oh, I know, but I'll let everybody else guess.
All right, Hope. I'm not seeing too much roll into the chat, so I guess you're up. When was it? Okay, we have a guess of 2003. It was actually the very first version of the Energy Conservation Code back in 2000. Um, it's funny too, the idea of air leakage has actually been in the code even longer, just not the concept of an air barrier necessarily. But that's been in the code for a very, very long time. You can date that back to old BOCA stuff, old ICBO stuff, Uniform Building Code, all that good stuff. You can date it back all the way to there. And old ASHRAE documents as well. I mean, they talk about it as far back as the first 90 standard in 75, but they don't really identify air barrier until you get into the 2000s, until about 2007 or 2010, I think. But yeah. Oh, great question. Yeah, 2012. Actually started in 2000, very first edition, quite some time back. Great questions. And so one thing I want to highlight for you here is how important air leakage is in our ability to facilitate a good wall assembly. So DOE did a study, and they looked at, I think it was 8 states. Oh yeah, it says right down here. Sorry, I'm trying to call it up by memory, and it actually says they did 8 states, and they found that about a third of homes didn't meet the air leakage standards for what they were using there, and it was accounting to 25 to 40% of the energy used for heating and cooling in typical residences. I don't know about you, but I don't like setting my money on fire, and that's exactly what you're doing if your house is not well air sealed and you turn on your furnace. You're literally heating the outside, right? And if we can avoid that, we absolutely should. We should try and keep as much of that heat in the house as possible when it's cold, and vice versa. If I'm cooling the house, that is expensive these days. There's no getting around it. So let's keep as much of that in as possible. So these are your typical air leakage points. And this is out of the commentary in R402.4. And I think it's just a really good example of where to think about the house. Now, I know that you guys have your checklist as well, and I think that this is a really good thing when you're training inspectors to go over with in terms of a good resources. Look at what why we're looking at these places. Well, these are the places, when you think about it, that have either joints, dissimilar materials, penetrations. There are places where we are intentionally poking holes in this wonderful box that we made that was supposed to be fully air sealed. So we have to be careful with it. So one of the things that we want to debunk right now is that insulation is typically not an air barrier. Insulation's job is to resist thermal conductance or conduction, right? But airflow is typically not its job, right? That's where we get the problem of wind washing. So if you're getting wind to go through your beautiful pink insulation, it's taking all of the air that it was trapping, all of that R value that it built up. So, how do we do this backwards in existing buildings? Man, that is a great question. So one of the first things that you need to know, right, or one of the things that we need to think about is, what's the opportunity to open up this wall cavity or this assembly, right? Are we stripping off siding and then we're going to replace some sheathing? Then we only get the one side of this when we talk about maybe the weather resistive barrier, maybe we have some exterior insulation, some continuous insulation on the exterior, and sealing those joints will help produce a more sealed building. If we're doing a remodel, right, we're gutting the kitchen on the inside of the house and it abuts an interior wall, something like that. Well, then we use that opportunity to try and make sure that we have proper evaluation of what is our total assembly, right? It's a good thing to talk to the contractor about and say, do you have any exterior insulation, right? Oh, no, it's just cavity, it's just pink stuff. Okay, well, how's the pink stuff doing? Well, we found some rot in some places. Well, that's a good cue for you. It means it probably doesn't have great air sealing. So that's a great thing to talk to them about. Okay, well, let's take a look on the exterior. As you do this, let's see if we can seal that up better. We're going to replace that insulation, right? And we'll see if we can do some caulking, maybe some spray foam in some areas if we're going to be pulling some of that insulation out. So this is a tough question that's really dependent on, the depth of the remodel. How far are we looking back? Because we don't want to just arbitrarily expand work for people, right? Our job as code officials is to try and make it effective and easy to be able to build your house in a way that's safe and affordable. Same thing with your business. So we don't want to just go around saying, well, you gotta look through the whole building, right? But if we see evidence, if you see something, let's say something, right? And so similarly with the air barrier, right? If we see that it's supposed to be on all 6 sides and it clearly isn't because we're getting dust, debris, when we pull back the insulation, we go, oh man, that's not performing well. That's not doing its job. Maybe it's an opportunity to seal that from the inside with a little bit of spray foam or some foam sealants or things like that. So What's one of the biggest myths that we have? It's that insulation stops the movement of air. It does not. Insulation, it traps pockets of air, right? I love this example of the jacket, right? It creates those stagnant pockets of air that create R value. Meanwhile, an air barrier stops the scrubbing. And what I really want to point out, because I think this parka example is perfect, and I'll explain why. So you look at her jacket, and I want you to think about like the nice parka or winter jacket that you have at your house, right? That you might pull out here in a few months. And it's got all these little features that we take for granted, right? It's got the little Velcro around the sleeves that you can tie up around your glove. And that makes you're using multiple materials, right? You're using Velcro and the jacket itself to create continuity of the assembly in a place where you have a joint. You have dissimilar materials, right? That is a perfect example of thinking about an air barrier. It has a little flap with the Velcro over the zipper because, again, we have a joint that we have to protect and we have to think, don't bring. Hey, it's all I can do, Hope. I like it cold. I'm one of those folks that I could pass on the worst days of summer. I can't wait till it's elk season. That's my take, but neither here nor there. But the barrier here stops the scrubbing of air and it seals at all those joints. And that's why it does its job really effectively. So when you think about this, if you ever have to express this to maybe that homeowner that's just not wrapping their head around air barrier and they're going, well, my visqueen is the air barrier. Whoa, no, 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 no. I understand that we're using the visqueen as your vapor retarder. It's part of your vapor retarder assembly, but it is not your air barrier. Your air barrier is specifically a material that you're sealing everything else to. The biggest thing to take away from all of this is that you're about controlling the airflow here, and you're doing it in a way that is durable and continuous. So when we look at air barriers here, right, we look at 402.4.1.1, and here is the list, so to speak. These are the big components in the table. Narrow cavities was one of the big ones that was added in the 21. It's funny, narrow cavities being a big one, space is more than less than 1 inch, 1 inch or less, I should say. That need to be sealed, and you're sealing them with, foam sealants, things like that. We're saying don't pack them in with insulation anymore. Make sure that you have air barrier that's continuous in those places. But the insulation isn't going to pack in and prevent that. It's just creating thermal bridging. Basically, that's the reason that it was added, right? But this is your chart that you want to go to, and you want to treat it like your checklist, so to speak, when you're looking at your plans. Because if you're getting plan details on all of these, you're going to be a lot more successful, which actually is going to bring us soon to resources, where I'm going to go over some cool stuff that we have for you. So, air barriers are systems. Those systems are about control, and it's about controlling where airflow moves. This is also a place where we can directly tie the features of the energy code to life safety components, because controlling airflow has been something we've been doing a long time. Think about your garage to residential separation. That's to prevent CO2, right, from entering, or carbon monoxide, I should say, not CO2, but carbon monoxide, from entering the house, right? That's one of its key purposes, is to prevent people from dying. And it's an air barrier. That's all it is. It is an air barrier. It's sealed drywall that's creating a seal in that room and saying, okay, it's isolated and this cannot pass. This gas will not be able to pass freely into the rest of the house and kill people. And what's keeping them alive is a passive system that's an air barrier. Well, it's the same thing that we're trying to use to encapsulate our insulation. So we can use air barriers for a number of other things here, right? Reducing pollutants from entering a building, mitigating fire and smoke intrusion from the exterior of the building as well, depending on where that air barrier is installed, reducing smog, and keeping your air conditioned, where you want it to be, not letting it leave the building. So now we're on to resources. We're on to the last third of your class here, but I would say is truly the meat and potatoes, right? So we put a lot of holes in our air barrier here, and I really want to point to you first and foremost that you have a list of good materials in there. And of course, these materials, right? This handout for this class will be headed over to you as well, Richard. But this provides a nice list and nice details to kind of go over where those need to be, where those need to go. And like we said, picture's worth 1,000 words. 402.4.1.1 requires details, and so does 103.2. It points to specifically air sealing details. So in two places in the code, you have pointed out you need good plans. And so we bring to you a wonderful guide to be able to help provide that information. And so with that, let me drop that into the chat here. I'm so sorry. I thought I had it queued up on my desktop here. There it is, hiding in a folder for me. Hmm, Here we go. All right, I'm dropping it in the chat, and you should be able to download it here in just a second from the chat and take a look at this wonderful guide that we have for you that breaks down piece by piece. And I'm actually going to show it on the screen here. What you need for plans. So, yeah. This guide is meant to provide you with a handout that you can, and yes, Hope is exactly right. We will also send it out by email. What I'll do is put together a zip file of all the resources I'll be sharing with you today, and you'll be able to take down whatever you like, whatever you want to use. But this gives you a nice breakdown of the places where you would be looking at this, some real life pictures to go over it, the materials lists out of the code for you from chapter 4 of the commercial code is actually where it's laid out in here. It's not in the residential code directly, but the materials are exactly the same. Some explanation of how it's different from a vapor retarder, so that way you can share that with folks that might be a little confused on the issue and thinking, people oftentimes, confuse those two items or use the same language to describe it. And here you have actual details that you can either allow people to use directly or they can use as a sample so they can draw their own. So folks that you have coming in, they have never drawn a detail for an air barrier before in their life, and they have no idea what you're talking about. Well, great. This provides them a toolkit to be able to say, okay, I'm going to use these and I'm going to do it exactly like you tell me to, or I'm going to trace this and then I'm going to draw my own. And we go through each item that's listed throughout 402.4.1.1 for you. So I hope that's of good value to you. And expect another resource coming. I was hoping to have another one done for you that we've been working on for some other states, and I'll need a day or two more to finish it, but hopefully we'll be sending another one out going on over the types of barriers, hopefully a good summary of kind of the content of this class. Some of the other places that I want to point you to in water resistive barriers is Building Science Corporation. That is Joe Stebrick. That's the guy that I referenced earlier. He's got some really good stuff, especially on the non-conventional construction. A lot of the articles, basically everything they have posted there is free to use. Also, never discount, obviously, your manufacturer installation instructions, right? Those are a key resource and place to go to. So I have, for instance, DuPont's Tyvek water resistive barriers guide, right? And you notice there it also says air barriers because it can be used as an air barrier. And this is one of those places where setting the expectations for your inspection process to say, have those on site, especially if you want to use it in this format, really will pay dividends as you get better plans for discussing this issue of getting better air barriers. And then ICC as well is also providing new stuff out all the time. I know that some folks have moved over to the digital codes. Digital codes now has a graphic search tool that you're able to use. So if there's a particular detail you're looking for, you can actually do a search on that. There's a lot of cool stuff coming out of them. The next one I want to hit for you is vapor retarders through the Applied Building Technologies group. So I'm going to bring this over onto the screen here. Now this is really cool, and I am going to drop the link in the chat so you can follow along if you like. And so this is a calculator that lets you figure out whether or not your vapor retarder is allowed to be used, and it basically runs a full calculation on a particular wall. So we're going to say that we're doing a 2021 IRC and IECC residential. That's what the R means there. We're going to say it's in climate zone, let's say 3B. We're going to say we're going to use vinyl siding. We're going to have some exterior insulation. Why don't we have an R5 of exterior insulation? We're going to use a 2x4 wall with 7/16 OSB, 16 on center framing, We're going to say we have a cavity insulation. If I have an R13 wall, or excuse me, if I have a 2x4 wall, we're going to say an R13 with a 1/2 inch chip finish. And check it out, guys. Right over here, we actually get the content, whether it passes or fails with which class of vapor retarder. And take a look. You can't use a class 1 vapor retarder here on this assembly. That would be your visqueen. If you do, then you're trapping moisture in that wall. So if you've got plants examiners that are learning how to do this well, hey, this is a great tool to have them run walls in or to have people send them to you. And here's how you can have them send them to you. So first of all, it does a thermal check on these walls as well, kind of similar to a res check tool where it says, hey, these are the code requirements for that area or the U factor. This demonstrates that it's compliant. It does a downloadable PDF as a report that you can submit with your wall assemblies and say, okay, this works, this doesn't, we're going to do a class 2. So this is a great way to be able to present that, and it's got signature lines for the person that prepared it. So you can have it submitted in the course of the rest of the documents and resources that you need in order to be able to do your plan review. It's a wonderful tool, and I won't show it to you because we're running low on time, but if you go to the site, they also have a steel wall calculator. So you can use this for commercial as well. For most of your typical wall assemblies, they have what you need in order to be able to go over this. So two really good products out there from this particular group. Next, I want to go over to your plan checklists from Continuous Installation Organization. These are some really cool things here. Download them, and let me actually go back and drop this in the chat. I forgot to do that. There we go. So continuous installation here has some really cool documents on how to do plan checks for continuous installation based on your prescriptive method, your performance method, for breaking down each component. And so you can tie this back to your discussion with your installation overall, and your vapor retarder, right? So this is one of those key places that this can help you go over. And I know we're getting close on time. I want to be, as quick as I can to get you everything that we talked about, because I think that it's important here. And then I believe fact sheets is where we want to go now. Let's see here. Moisture control for wall assemblies. Let me toss this one in the chat next. So I also want to reiterate, this is one of those industry groups that as a whole represents all of continuous installation. So you have a lot of product agnostic stuff here. There's no doubting the fact that they are part of the group that wants to sell, continuous installation. So they're going to help push that. But I just want to make it clear that it's not product specific. Chris, go ahead, sir. Oh, absolutely. Yeah. So I did put it in the chat, and because it's a PDF, Beth, I will have to email it to you, but I will get it out to the group after we are done. So I will make sure to get out the Excel guide to you as well. But the format just won't let me do it as a link. And then Chris, go ahead, sir. Oh, let me see if I can get you off of mute. There we go. All right, Chris, you should be allowed to talk if you want. Mm. You're not coming off of mute, Chris. So if you want, go ahead and toss something in the chat as well, and I'll try and get to it that way in case you can't hear me. And then last but not least here, let's see here. I believe this is where we want to go. Nope. There we are. So for those that are working with more and more items here, like water resistive barriers on exterior insulation, they do have fact sheets specifically on how to work with these two, because a lot of folks have been concerned about how do I make sure that I have continuous water resistive barrier while integrating that exterior insulation. And as you can see, there's multiple foam sealants depending on the product that are out there, and some step-by-step guide information that they have available to you to go over the same topic. And so some really good stuff, especially for folks that are getting their feet underneath them for the first time. Installers that maybe haven't taken a look at this. And some good and bad installs as well, which I really do appreciate the fact that they include stuff like that. So you can see that left and right, hey, this is how we want this to look. This is not how we want this to look. And then I think last but not least, I wanted to show you this tool, which is from PNNL and Build America, in which you can go to, let's drop over to New Mexico. Let's say we're in that 4B climate zone or 5B. There are actual assemblies that you can point to at are downloadable that are also agnostic. I mean, these are put together essentially for DOE use that shows a vented cathedral wall ceiling. So if you have somebody that can't draw details or doesn't know quite what you mean by this, you have a full library of items that you are able to use to demonstrate how you use mixed systems, all out of the 21 IECC. So you have multiple items here, ICF walls, double walls, so some complex construction and some typical light frame as well. So some very cool stuff all associated in this space. Let me go back to the presentation now. One of the things I was going to tell you about as well in that calculator from Applied Technologies, there is a way to look at just the permeability of all of the items associated in the assembly. There is some resource out there, and I will follow this up with the email with the guide as well. We've got a few other items that we've had out for a while on the 21 on air barriers that I'll be sharing with you. I took a look at the New Mexico website there, and I found some stuff to be a little out of date, so I'm going to see if I can get that updated. So what'll go out with this group will be to everyone who attended the class today will be basically a downloadable zip file where you can get all of the materials that we've put out on air barriers for the past few years. And I'll include this in it as well if you want to look into sort of particular permanence of certain cladding materials. But it'll be some of these items right here. So some of you guys might be familiar with this. We've taught classes off of these before, and we've had these up for a while. I just noticed that some of the links weren't quite working for me, and I didn't want to give you guys bad links. So I'm going to make sure that everything's in one package, and it'll all go to you guys sometime later today after class. But these go over some of our commercial requirements for air leakage when it comes to inspections, when it comes to specialty areas like vestibules, operable openings, loading docks, good stuff like that. And then we also have our energy field guide out there for you as well. This one was published last year, and this will be one of the other items I'll be following up with you. So in conjunction with that plan review guide, this one goes over in real life, how should we be checking for this? Like I said, we know that you guys are already keenly aware of this with the checklist that you have to use through the state. And making sure that you guys are following that to the T. This is just supplemental information that hopefully makes that job a little bit easier for you. So we're about wrapped up on this. I wanted to make sure that you guys are all aware that the wonderful Miss Hope Medina is coming to Hobbs in the near future. Hope, I don't know if you want to jump off a mute and talk about this training.
Yeah, so in Hobbs, we are going to have an all-day class. The focus on it will be commercial energy. So in the morning, we will look at the components that you'll find for the thermal envelope, and the afternoon session will focus on the mechanical provisions and the lighting and electrical provisions. So we would love to see everybody there. Send your people in the group, send the contractors, builders that you work with, and we'd love to fill that room and, have to find chairs.
Yep, come on out and see us, please. As we wrap up today, please remember your surveys. It is super important to us to do the surveys. It helps let our wonderful corporate overlords know that we are doing right by you, or if we're not, where we can improve, which we are always happy to, take that into consideration. So if there's something else that you'd like out of this class, or something that you want us to highlight in the future, anything like that, please make sure to put it in there. We always want to make sure that it's your time and it's getting used effectively. I am not on this screen. This is Hope Medina and Josh Harmon, your regular host. I really hope that you guys find this stuff useful. And please follow up with us as well. If you get into some of this stuff and you go, hey, I wish we had a document about X or Y or Z, we got to make this stuff anyway. So we really want to hear from you guys what would be effective for everyone. So thank you very much for your time today. And with that, we are wrapped.
Yeah, I'll throw one more thing out there. If you're interested in doing a friendly visit, where we just kind of have a conversation and you want to give us your 2 cents on things and resources that you need, reach out to us. We would love to have the conversation.
All right, all. I've got multiple classes lined out through the rest of today till about noon, give or take. So after I'm done with those will be when you can expect to get those emails from me with the additional resources. So sometime this afternoon, once I get freed up. So